Welcome to the MOOCs course Mechanical Unit Operations. This particular lecture we will be discussing storage of bulk solids. Till now we have seen why the size reduction is required for a given bulk solid, especially when we are doing some kind of operations involving only solid phases, and then what are the kind of size analysis methods, and then what are the kind of size reduction equipment available. So, different types of size reduction equipment and all that we have seen, and each category of size reduction equipment, what are the commercial designs that are available, those things we have seen in the previous 3 modules. This is the 4th module. In this 4th module, we will be discussing storage and conveying of bulk solids. So, once you have done the required size reduction, how to store them and then how to convey them for a given operation which is involving solid phases interacting. Right. So, the title of this particular lecture is storage of bulk solids. Now, before getting into the details of storage of these bulk solids, what we do, we try to see how different are these solid masses from a fluid perspective. Let us say when you have a fluid, so when it is flowing, what are the kind of things are happening? So, similar kind of things are happening or not, those kind of things. What are the similarities or dissimilarities compared to the fluids when they are flowing in a kind of a given geometry. So, considering those factors, here we first see what are the kind of different type of different kind of properties, what are the kind of similar properties considering the in a comparison with the fluid phases. So, those similar properties of solid masses compared to the fluid phases that we are going to see now, and then after that we will be seeing the distinctive properties of solid masses which may be very much different from a kind of a given case of a fluid. Okay. So, properties of masses of particles. These masses of particles, in the sense whatever the size reduction we have done, we have taken bulk solids and then we have done a certain kind of size reduction. So, then we may be having small grains or something like that, very small size particles, etc. So, we are discussing the properties of those masses of particles or solid masses particles, those properties we are going to discuss now. If you have a dry and non-sticky particles in your sample, or if your sample is primarily dry or non-sticky, then it is possible that sample may have many of properties of a fluid. So, whatever the fluids have the properties, similar kind of properties, these dry and non-sticky particles, solid masses may have. What are such kind of property? For example, so when you have a fluid, they exert pressures on the solid container walls, sides and walls of the container. So, exert pressure on the sides and walls of container is there in the case of fluids, and then the same property we can experience, we can see here if your solid and mass is a kind of a dry and non-sticky material. And then fluids, what happen? They may flow through certain kind of given openings, right. So, same is possible, same is true here in the case of dry and non-sticky solid particles as well. So, they also flow through opening as a kind of a fluid does. Okay. So, these kind of some kind of properties which are similar compared to the kind of fluid, but however there are a certain kind of properties which are very much different from a kind of fluids, something like that. Masses of particles differ from liquids and gases in several ways because particles interlock under pressure in general and cannot slide over one another until applied force reaches an appreciable magnitude. But in general, if you have a kind of Newtonian fluid, what happens if you are applying pressure, the flow can be convenient and then more faster flow may be coming in general for a Newtonian fluid. Let us not go into the non-Newtonian fluids and all that. If you take a simple Newtonian fluid, what happens? If you apply pressure, the flow may be more comfortable, but in the case of solids, if you gradually increase the pressure, it is not necessary that flowability of this material increases. That depends on the size of the grains that we are handling. Let us say if you have a very small size grains, then what happens, when you apply pressure or gradually increase the pressure, so rather increasing the flowability, the particles will become compact and the kind of the packing, it become kind of more strong packing kind of will take place, and then the material may not flow through. So, that is what it mean by like particles interlock under pressure and cannot slide over one another until applied force reaches an appreciable magnitude, okay, which is the dissimilarity compared to kind of Newtonian fluids. In general, Newtonian fluids comfortably flow if you increase the pressure. Further, granular solids and solid masses permanently resist distortion when subjected to a moderate distorting force. So, if you have a Newtonian fluid, when you applied a kind of a force, then they will continuously deform as long as the effect of that force is existing on the kind of fluid elements. But here in the case of granular solids or solid masses, as long as the force, that external force that you are applying for the distortion, if that distorting force is under the small and moderate range, the granular solids and solid masses permanently resist distortion and they will not flow. However, when the applied force is large, then the failure may occur and then one layer of particles slide over another and then may start flowing. However, between the layers on each side of the failure, there is a kind of appreciable friction. Let us say if you have a kind of layer of the solid, so when a fluid layer is there, then another fluid layer is there, so then they can move comfortably with less resistance, and then that resistance is a kind of viscosity of the fluid, right. So, that is kind of things is there, and then is in general in Newtonian fluid this resistance is a kind of friction is a kind of between the fluid layer is very small, whereas in the kind of solid end masses, when the applied force is strong enough, large enough, then a kind of distortion will take place and then layers will slide over onto other, but when they are sliding onto other, they may flow, and then when they are flowing, they also have a kind of a significant friction between the layers on each side. On the if this is the one side of the layer, this is the other side of the layer, between these two layers there will be a kind of a significant appreciable friction would be there. Whereas in the kind of fluids, that friction is a kind of very small, and then it is same for either of the fluid layers. And then this friction whatever between the fluid layers is there, that is that is can be represented as a kind of viscosity. But here in the case of granular solids and solid masses, the friction may be different on each layer, but it will be there on each side of the failure, there is a kind of appreciable friction. So, these are the kind of some common properties with respect to the fluids that we have seen. What are the similarities or dissimilarities, especially compared to kind of fluid properties we have seen. Now, we see some distinctive properties of solid masses, right. We see some details of these solid masses, right. What are their specific properties, distinctive properties which are making their storage and conveying very much different compared to the kind of fluids cases, as I mentioned at the beginning of one of the introductory lecture. The storage as well as the conveying of the solids is a kind of very much difficult compared to fluids, or it is not as convenient as in the case of fluids. So, why it is, what are the kind of things that we have to consider under when we see about the storage and conveying of this kind of solid end masses. Some of the properties that we have already seen, size, shape factor, etc., and then density, and then surface of the properties, these kind of things we have seen. So, we see some other properties which make the solid masses or the storage of the solid masses and or the conveying of the solid masses is very much different from a kind of a fluids perspective. First of all, in what happens in the kind of fluids, the pressure in the fluid is everywhere same as long as the fluid is Newtonian, right. So, whatever the pressure is there within the system, the pressure remains the same, it is constant everywhere, right. So, some distinctive properties of solid masses. First one is the pressure is not same in all directions. Let us say if you have a kind of a solid masses like this, right, in a container or in a kind of tube like this, or grains are there in a kind of things which may be you are taking to the operations, or you may be taking to the kind of storage unit, something like that. So, let us say if you are applying pressure here on the top surface for example, so the pressure would not be same in all direction. The pressure let us say this pressure would be distributed in all directions. Indeed, that will be distributed in all directions, and then that distribution is not same in all directions. So, the pressure in this direction may be something, and then pressure may be something else, and then pressure in the other direction may be something else, pressure in the normal direction may be something else. Like this, the pressure is not same in all direction. That is what one of the primary most important property of the solid masses. The pressure applied in one direction creates some pressure in other direction, but it is always smaller than the applied pressure. So, let us say pressure, as I mentioned, when you are applying the pressure on, let us say, on this particular, that may be creating or distributing the pressure in the other direction as a kind of arrows showing here. So these kind of pressures, like now the pressure distribution is very different from one location to other location within this solid masses, whether it is in container or in a kind of channel that is flowing. So the applied pressure is in general very much higher, or the pressure which is being created or distributed in the other direction, that is a kind of smaller compared to the applied pressure. Let us say applied pressure is P. So, or the pressure in other directions, let us say Pi, Py, Pj, Pk, or in a different direction it is being distributed with certain kind of angles also are involved, let us say. So, this Pi, Pj or Pk, whatever are there, they are smaller than the applied pressure P. So, let us say the pressure that is being distributed in these three directions, or let us say Pi, Pj and then Pk are there. So, all of these things are smaller than the applied pressure P in general. Then it is minimum in the direction at right angles to the applied pressure, or let us say if you have a kind of this is the solid mass that we are having here. I am just let us say you are applying pressure here, right. So, now this pressure is being distributed in all possible direction, and then it is having different magnitude each direction, but however each direction the pressure that is being distributed or transferred, that is smaller compared to the applied pressure P, but where in which direction it would be very minimum. So, let us say if you are applying this direction here, so it is in the normal direction or at right angles to the applied pressure, it is going to be very much smaller. So, that is, let us say in the normal direction the pressure is Pn. Pn is very much smaller than the applied pressure, and then this Pn is in general minimum, but however it is not negligible. The Pn that in the normal direction, that pressure, that normal pressure, now we can call it as a pressure, or the pressure that is being distributed or created at right angles to the applied pressure. Let us say if this is your the pressure that you are applying in this direction. So, whatever the pressure that is along my hand, so that should be taken as a kind of normal direction. So, the pressure in the normal direction whatever being distributed or created, so that pressure we can call it as a normal pressure, and then this normal pressure is going to be minimum compared to the pressure distributed in the other directions, like this or like this or like this, something like this. Okay. Compared to the applied pressure, the pressure that is being distributed to the all other different direction is definitely small. Amongst all, the pressure that is distributed at right angles to the applied pressure is going to be minimum one. Minimum, but it is not negligible, and it is very much important as well. Why important? In homogeneous masses, the ratio of this normal pressure to the applied pressure is a constant K. That is the reason it is important. It is important, having its information is very important, because it is a kind of characteristics of the material. Solid masses that especially you have taken, it is a characteristics of that solid and mass. For a given material, if it is a homogeneous mass, that is you need to have a kind of same material, you cannot have a kind of mixture of solids. If you have one single kind of homogeneous mass, then the ratio of the normal pressure to the applied pressure is going to be a kind of constant, and then it is characteristics of the material. So, that is K is nothing but Pn by P as per our notations that we have used. Okay. This constant depends on the shape and interlocking tendency of the particles on stiffness of particle surfaces and how tightly the material is packed. It depends on the several kind of factors. First of all, the shape of the that material that you have taken, or the grains whatever you have taken, and then interlocking tendency of the particle. Some particles easily interlock, some particle does not interlock. That depends on the surface as well as the shape of that material. So, some kind of materials are having needle like kind of material, they can easily interlock. If you have a kind of almost rounded ground particle kind of things, so then they may be having less tendency to interlock, right. And then stickiness of the particles is also a kind of a very important factor that is affecting this constant K. And then how tightly the material is packed, how tightly the material is packed, that is also going to be a kind of a very important factor, and then it is going to have effect on K. So, K depends on the shape and interlocking tendency of the particles, stickiness of the particles, and then how tightly the material is packed. This constant is nearly independent of particle size. However, until the grains become very small and the material is no longer free flowing, up to that point it is it may have some kind of effect. However, that is it may depend on the size of the particle, it may not depend on the size of the particle. If the size of the particle or grains becomes very small, that the becomes become no, the material or grains become no more free flowing nature, then then under those conditions the K constant does not depend on this size of the particle. But however, particle size is slightly bigger, and then they are still free flowing, then we can say kind of that size of the particle is also having effect on K, or the K depends on the size of the particle as well. So, let us say we have the wheat. So, when we take the wheat and in a container and you take out of the container by opening or by tilting the container, they can comfortably come out. They have a kind of free flowing nature as long as the wheat is properly dried. Okay. And then if you crush it to smaller sizes, then still it may free flow, right, crushed wheat kind of thing. But if you grind it such a way that when you get the flour, the wheat flour, what happens, it does not flow comfortably, it will not be any more free flowing. That is what it means by like wheat or crushed wheat which are under the free flow conditions. So, under that conditions the K constant depends on the size of the material as well. But once the wheat is crushed to such smaller grain size that you get the wheat flour, then that wheat flour is not free flowing material in general. So, under such smaller size the K does not depend on the size of the particle. However, one can say this is nearly constant or independent of the particle size. Then the shear stress applied at surface of solid mass of a particles is transmitted throughout a static mass of particles unless the failure occurs. So, not only the pressure, whatever the shear stress that is applied on a surface of solid masses, that is also going to be transmitted throughout the static mass of particles unless the failure occurs. Then the density of the solid masses is also very much important, and then it is a kind of distinctive property. So, the density of solid masses are masses of particles, smaller particles, they vary depending on the degree of packing. In general, if you have an individual particle if you take, and then what happens, the density of that particle is a function of temperature and pressure in general. But if you have a kind of a packing of the solid material, so solid material if you pack in a kind of particular manner, so then that density is not a function of temperature and pressure, that should be noted, right. So, density of each individual particle is function of temperature and pressure, but the bulk density of mass, the solid mass of the particles, is not function of temperature and pressure. However, density of the bulk density of the solid masses is minimum when the when the mass is loosely packed, and then density or the bulk density of the solid masses is maximum when the material or the particle is packed by the vibrating or tamping, so that they are very closely packed. So, tightly if you are packing, the bulk density of the solid masses would be high. That is, per given unit volume, you can accommodate more mass of this solid by doing tight packing kind of thing. If you are doing loose packing, you can accommodate less material, so then the density would be small in the case of loose packing, and then density would be large in the case of tight packing kind of thing. However, density of this bulk material, solid and mass material, is independent of pressure and temperature, though the density of the individual particle is a function of temperature and pressure. For a mass of tightly packed particles to flow, let us say for a mass of tightly packed particles you have taken, and then you want it to flow, what should it be taken? Like initially you packed very tightly with a compactness in the kind of container, and now you wanted to take out that material, or you want to flow that material so that you can use it for a kind of required operation, subsequent operation. Alright. So, it will not be packing easily in general. Like if the material solid grains, especially if the size is very small in microns or something like that, if you pack those materials, under high pressure or the, kind of by tamping or vibrating, if you closely tightly pack it, that material will not flow comfortably. So, then if you want that bulk material to flow, whatever the tightly packed bulk material, if you want to flow, what you have to do? You have to create a kind of dilation. You have to increase its volume so that a kind of dilation takes place, and then that particle or the solid mass can flow comfortably. So, that is, it must increase in volume to permit interlocking grains to move past one another. When you are tightly packing, so there will be a kind of more stronger interlocking between the particles like this, something like that, and then they may not flow comfortably. Right. So, then what you have to do? You have to increase the volume of that material so that the interlocking can be relaxed, and then the particles may slightly move on one onto other, and then particles may comfortably flow. That is a kind of a dilation you have to generate. Without such dilation, flow is not possible. That is what it means by. Then sides of granular solids piled up on a flat surface are at a definite reproducible angle with the horizontal, and this reproducible angle is known as the angle of repose. Right. So, let us say you can do this experiment. You take wheat and then you take rice, and then you pour them on a kind of horizontal surface, right, carefully like this. So, and if this is a surface, so whatever the time you pour it, so these sides they may be forming a kind of piling up like this, right. So, these sides, whatever these sides are there, these sides they are always going to have a kind of a reproducible angle. Whether you take a kind of 1 kg of wheat or 100 kg of wheat, as long as the material is same and then surface is horizontal, wherever you pour, you may get this angle reproducibility. The angle is reproducible, and this angle is known as the angle of repose. And then all material will not form or piled up with a kind of constant same angle. So, some material if you pour on the surface like this, so you may be seeing that they are piling up, spreading more like this, and then they are kind of piling up with a less height, something like this, so that this angle is also less. Here in the this case angle is less. So, let us say here theta 1, let us say here theta 2. So, theta 2 in this case less than theta 1. Let us say second material is rice and then first material is wheat. I am not saying this exactly the rice and wheat, the rice angle would be smaller compared to the wheat angle, but for example, say you have taken wheat and piled up on a surface, and then you have taken a rice and then piled up on a horizontal surface, or you poured on a horizontal surface, they are piling up. So, if you see their angles, like they take these angles, and the sides, you take these sides and then try to measure the angle with the horizontal for either of the cases. Since the material is different, they may be having the different angle. Okay. So, but as long as the material is same, this angle is going to be same. So, this is a kind of very important angle, and then it is used in kind of designing of storage equipment for these solid air masses. So, there these angles are in general kind of useful. Okay. So, that means indirectly rise when you pile up on a surface, it is going to pile up in with so that its sides are forming a kind of reproducible angle. So, this angle is called as the angle of repose of the material, and then for free flowing granular solid it is often 15 to 30 degrees. And then solid masses are classified as cohesive and then non-cohesive particles depending on the flow properties or depending on these K values, whatever that we have seen, that K is nothing but the ratio between the normal pressure and then applied pressure. So, based on that one we can define this material solid masses as a kind of cohesive particles and then non-cohesive particles depending on the flow properties. We have a cohesive solid particles such as wet clay, highly concentrated slurries which are reluctant to flow through opening. In general, you have a, let us say, container, big container, at the bottom you have a opening. When you open the wall opening, then what happens, the material should comfortably flow. But if the material, that solid material is a kind of cohesive solid material or wet clay or high concentrated slurries, they may not be flowing comfortably, and indeed they will be reluctant to flow through openings. So, for such cases the K value, that K value is close to 0, the ratio between the normal pressure to the applied pressure is going to be 0, that is the pressure is not going to be distributed in almost all directions. In all directions it is not possible. So, especially in the normal direction, when you are applying the pressure here, the pressure is going maybe distributing in this other direction here, like with this angle or this angle like that, but in the normal direction the pressure may not be created or may not be generated or distributed. So, that ratio, the K would be small or close to 0 for this kind of cohesive solid particles. But non-cohesive particles such as grain, dry sand, plastic chips, etc., they flow freely out of the storage bin, and then for them this K value is between 0.35 to 0.6. Now, we see storage of solids. Having these solids, distinctive properties of these solids known, so then it is again becomes a kind of question, so how to store them and how to convey them. So, first we start with the storage of solids. Storage can be done in a bulk storage or kind of bin storage in general. Bulk storage is in general used for when you have a kind of tons of hundreds of tons of material is there. So, then in general you store them in open outdoor storage kind of thing, right. But if you have a kind of valuable or too soluble materials are there, then in general you store in a kind of bins or silos, something like that. So, those things we are going to see in this slide. So, storage of solids, it can be done bulk storage and bin storage. So, first we do bulk storage. Bulk storage, in general many solid masses which are coarse such as coal or crushed minerals, etc., that we get from the natural resources from earth, whatever we get the big lumps, we crush them into kind of a smaller particle by primary crushers. So, those crushed materials are sometimes directly run away from the mines, whatever material is there, that also you can store outside in large piles without any protection from weather. So, so these kind of things are can be done, this kind of bulk storage can be done for such kind of material, where you do not need a protection from the weather in general. And then when you have a kind of a huge amount of material, tons of material is there, something like that, so then we can use so the examples in general we can say as a kind of coal directly from the mines, whatever the coal that you get, you can pile them up in a kind of large empty space and then leave them as it is without any protection from weather in general. Though it is not advisable, but however the point of mentioning is that we do not need any kind of special protection from the weather. However, such type of outdoor storage is very economical, especially when hundreds or thousands of tons of material is involved. So, let us say in coals, daily from coal mines daily you get hundreds and thousands of several hundreds of thousands of tons of coal is digged out, mined and then taken out onto the earth surface. You cannot afford to have a kind of separate designated kind of storage equipment and all that. You will not able to have them economically, even if you could try to have. So then such kind of material may be piled on earth surface without any protection from the environment. So on requirement, these bulk solids are removed from piles by drag lines or tractors and delivered to conveyor or to process of interest. So let us say coal you piled on a surface on a empty free earth surface. So whenever you need to transport, you can use the drag lines or tractors and then load in a kind of lorries or a kind of trucks, etc. Then you can take to the process or location where you need to do process, or if it is already in the process, you can through the drag lines or tractors you can take them to the kind of process of interest where you may be doing the size reduction or something like that. However, such outdoor storage lead to environmental problems. Usually, as usual, it is possible. One of the primary environmental issue is that the dusting. Another one is that leaching of the solvents or fines and then getting into the earth surface, something like that, those kind of things. So what are the environmental problems such as dusting or leaching of soluble material from piles? But however, this can also be controlled. So dusting can be overcome by protective covers. Whatever the piles that you have, you can cover with a kind of protective cover so that dusting can be reduced. And then leaching can also be controlled by covering pile or by locating it in a shallow basin with an impervious floor from which the runoff may safely withdraw. The surface has to be impervious so that the soluble material from piles should not get into the earth surface and then cause a kind of soil pollution. So that way you can have a impervious floor and then pour that material and then cover them. So that way both dusting and then leaching can be controlled. Then bin storage. Actually, wherever you have valuable or too soluble solids, they are stored in general in bins, hoppers or silos. Small quantities are the material which are very valuable or too soluble, then they have to be properly stored in bins, hoppers and silos, but they may not be in a kind of huge quantities. They may be in a few tons or something like that. Not very hundreds of thousands of tons will not be there, these kind of materials. So if the smaller amount of material which are valuable or too soluble, then those kind of materials are in general stored in bins, hoppers or silos. In general, these equipment are cylindrical or rectangular vessels made up of concrete or metal, and then the silo is tall and relatively small diameter container. Let us say you have a container something like this. So very tall cylindrical container with a kind of opening here at the bottom, right. So this bottom is not exactly this way, but just for indication I'm mentioning. So these are usually called as silo, whereas other kind of container are there. They are not tall, but they are wide in general. So these containers are known as a kind of bins. So small d, here diameter is small in a kind of silos, whereas in the kind of bins the diameter is very large compared to the silos. Okay. Bin is not very tall usually, and then it is fairly wide as I've shown here. So by the design they are given different names, but the purpose is the same thing. They are used for the storing valuable or too soluble solids in general, like this. Okay. Then we have the hoppers. Hopper is a small vessel with a sloping bottom. It is for temporary storage before feeding the solids to a process. Let us say you have a heterogeneous reaction. So, the solid material that is going to be reacted with a fluid in a kind of heterogeneous reactor. So, before the reactor you will be having a kind of container which is called a kind of hopper, the container for the storage of these solids. These solids are properly processed and ready for the reaction or ready for the subsequent operation. So they are a kind of temporary storage, just feeding solids to a process, and then these hoppers are a small vessel with a sloping bottom. Small in the sense compared to the bins and then silos, the capacity, hoppers capacity is smaller, and then usually they are located just before the process where the solids are going to be processed. So, if you have a common hopper geometries, if you see these three different types of are possible. So, first one is the cylindrical container with axisymmetric flow conditions, like we have a kind of cylindrical vessel like this, and then we have a kind of sloping bottom like this, and then there is a kind of sufficiently bigger size of opening here. So, this opening is B, and then this angle we can see, this angle is theta, this angle is same either side. So, and then if you see, the flow is a kind of a symmetric flow. Flow would be there in this whatever the solids flowing out of them, they will be more or less symmetric. So, and then this in the kind of cylindrical coordinates, shape is cylindrical shape. So, we call it as a kind of symmetric flow. We are going to see their details again. So, then symmetric plane flow, here what we have this container rectangular. We have already seen that this equipment used for the storage not necessarily be cylindrical always, they can also be rectangular, something like this. So, these rectangular equipment are there, and then they are a kind of opening at the bottom, right. So, here also this angle is there, right. So, now this angle you can see here, this one. So, here again it is a symmetric, that is the opening is in a kind of at the center, it's in the kind of center. Here also opening at the kind of center, or the central axis whatever is there, that is same for the opening as well as the container, and then same is true here also, whatever the center axis of the opening is there, that is also a kind of center axis for the container, that's in the middle like that. So, that you can have a kind of a symmetric flow. So, here this is known as the symmetric plane flow, because its container is not in a kind of a cylindrical shape. Here it is, a container is in cylindrical shape. So, we call it as axisymmetric flow, right. So, this angle is a kind of important factor that that is going to decide how much pressure the solids are going to exert on the walls as well as on the floor of the container. So, this pressure is going to be very much important in designing of these hoppers, etc. So, those things anyway we are going to see in the subsequent lecture. So, the third one is the non-symmetric plane flow. Here again the container, we have taken a kind of a non-cylindrical kind of container here, right, like this, and there is a kind of angle here again, at what angle this sloping is there, something like that. So, the angle is, this angle is nothing but the sloping angle. We have a cylindrical container, to the bottom of that one there is a sloping bottom is there, that sloping bottom angle how much it is, that is this theta, right, and then there at the bottom there is a opening again for all of these things. Now, here the center axis for the opening is different, and then center axis for this container is different. So, that is the reason these kind of containers are known as a kind of a non-symmetrical plane flow containers or non-symmetric hoppers. These are the kind of common geometries, hopper geometries, these are possible. So, bins, silos and then hoppers are loaded from top by a kind of elevators. You have the elevators, you can pour the material from the top and then store them for the time that you wanted to store, and then they can be discharged from the bottom, usually done through the bottom only. Whatever the discharging is there, that is generally done through the bottom only for these bins, silos and then hoppers. Next, pressures in bins and silos is going to be very much crucial and important kind of thing. This one has to be careful while designing. This will be very useful in designing the silos and hoppers, etc. So, how much the pressure that is taken by the side walls of the container, and then how much and the pressure is taken by the floor, etc., those kind of thing, and then how much is the kind of foundation. The foundation is also there, so that foundation how much pressure is taking. So, which one is important, how to calculate, all of them are very kind of very much essential part in designing of these hoppers or silos, etc. So, those design things we are going to see anyway. So, first we see how the pressure in bins and silos is going to affect operation in general. Lateral pressure exerted on walls at any point is less than the predicted pressure from the head of the material above that point. Whatever the pressure in the container, whatever the pressure in the lateral pressure is there, not the pressure in the flowing direction, the lateral pressure whatever is there, that one can predict, and then that predicted pressure in general less compared to the lateral pressure exerted on walls at any point is less than predicted pressure from the head of the material above that point, as in a kind of liquid by the head, up to what head the material is fed. So, H rho g, like that, whatever the hydrostatic pressure that you obtain for the case of liquids, similarly from the head also we can find out the pressure. So, that is that is known as the predicted pressure. So, usually true lateral pressure exerted on the walls at any point is less than that predicted pressure from the head of the material above that point. And there will always be friction between wall and solid grains, and then this friction is going to be sufficiently large. Unlike kind of fluids where the friction is small. Fluids also, when they are in container, at the solids at the solid fluid interaction point, there will be a kind of friction. But in the case of solids, the friction between wall and solid grains is very much high. This friction is felt throughout the mass because the interlocking of the particles. Let us say we have a kind of a container like this, and these are a kind of given by the support foundation here like this, right. So, these are the foundation. Okay. So, now this hopper we have a material like this, the solid material whatever is there that you have taken here, like, and then there is a bottom. So, what happens here, whatever the, let us say I make some space for here. So, you have a kind of a solid material here, it is having some kind of friction with the wall, right, and then this particle is again connected or attached to some other particles like this. So, there will be a kind of interlocking of the particles again like this, right. So, the other direction also it may be having the friction between the particles and then wall. So, these particles are being connected with the other particles, neighboring particles, by interlocking or whatever the kind of things. So, what happens, whatever the friction that is the particle or the material solid particles are experiencing at the wall, that is also being felt throughout the material within the material because of this interlocking kind of thing. So, it is not that the only that layer near the layer of the material that is near the container is only experiencing the friction. Because of the interlocking, the material in the other area, this area also is being experienced. Whereas, in the kind of fluids, what happens, primarily the friction is experienced by the fluid layer attached to the solid surface, but that is not true here in the case of solids. That friction between solid and wall whatever is there, that is container wall and then solid material, whatever the friction is there, that is being experienced by the rest of the material as well, not the layer that is attached to the container wall itself alone, because of this interlocking of the particles. Then friction force at wall tends to offset weight of the solids in general. So, whatever the weight of the solids is there, that may be very much higher, but because of this friction, what happens, whatever the friction at the wall is there, that slightly offset the weight of the solids, and then it reduces the pressure exerted by the mass on the floor of the container. So, that way it is going to be a kind of a beneficial only. That is one way. whatever the friction that is there at the wall, the friction between the solid particles and then container wall, whatever the friction is there, that friction is experienced throughout the material because of the interlocking, and then because of this friction throughout the material, that offsets some of the weight of the solids, and then altogether it reduces the pressure exerted by the solid mass we are pouring, and it reduces the pressure by the mass on the floor of the container. You design a kind of container with a certain kind of design pressure for the, especially for the floor, and then if you pour on large material by somehow, what happens, that may break down, right? But luckily such kind of issues may not arise, because some of the pressure or the some of the weight of the solids is offset by the friction between the particles and then walls, so that reduces the pressure. So basically, let us say you have a kind of a container here, and then this is the kind of a floor of the container. So whatever the material that is there here, so that material, when you are taking more material here, so this is the weight, some of the weight is being taken away by the friction between the particles and solids. So overall the pressure that is acting on the floor, that is going to be reduced, because some of the weight of the solids is taken by the friction force at the wall, friction force between particles and the wall of the container. However, the vertical pressure on vessel floor or the packing support is much smaller than that exerted by a column of liquid of same density and height. Whatever the let us say you fill the container with a liquid up to height h. Now you obtain the hydrostatic pressure h rho g, how much it is. Now up to the same height, you take a solid material of the same density as a kind of liquid, and then by height, whatever the static pressure that you calculate, so that vertical pressure you calculate, that is going to be much smaller in the case of solids compared to the case of liquids. So that is, vertical pressure on vessel floor for packing support is much smaller than that exerted by a column of liquid of same density. So you have a kind of a same containers like this, right? So here you have taken liquid, you have taken solid, but the density is same here. You have taken up to the same height here, this height whatever is there, that h. So then here rho L, rho S, so rho L is equals to rho S we are taking. So h rho L g, h rho S g. So whatever the pressure, let us say here it is PL, let us say it is PS. So solids pressure is always going to be liquid pressure under identical conditions, as long as the density and then density of the solid and liquid are same. So that is what mean by vertical pressure on vessel floor or the packing support is much smaller than that exerted by a column of liquid of same density and then same height. Then actual pressure from solids depends on several factors. First and most important one is that on the value of K for a respective solids that we have taken. So the value of K is going to have a kind of strong influence on the actual pressure from solids. As I already mentioned, it is a kind of very much essential thing, and then this now in the later course we are subsequent lecture we are going to design these hoppers, etc. So we are going to calculate or obtain the expression for this pressure, and then we will be seeing this pressure is going to be a strong function of K. So actual pressure from solids depends on the value of K for respective solids, and then friction coefficient between solids and container wall, because that friction coefficient is offsetting some of the weight of the material. So it is reducing the overall pressure because of the solids. So whatever, let us say when you take 100 kg of solids, so whatever the pressure supposed to be exerted, let us say 500 kilopascal. but because of this friction, that pressure is going to be less than 500 kilopascals in general. So that is what it meant by, so that friction coefficient between solids and container again is going to have a kind of huge impact on the actual pressure from solids. So probably it may be reducing the actual pressure exerted by the solids that have been taken in the container. And then the way solids are placed in the vessel, that is also going to have a kind of influence on actual pressure from solids. And then if height of solids column is larger than 3 times the diameter of the container, let us say if your height of the column of that up to which you are filling the solids, okay, and then let us say diameter of the column or the container is d. If h is greater than 3d, then whatever the additional solids you pour in, that is not going to affect pressure at the base. So that is the important one. So when you have a design such a way that the height of the solids column is greater than 3 times the diameter of the column, then whatever the additional material, additional solids you take inside the container, that is not going to have effect on pressure at the base, that is not going to increase the pressure. Usually what happens when you take the more material, so definitely the pressure should increase. But as long as if you maintain the design such a way that the height of solids column is 3 times or greater than 3 times the diameter of the container, so additional solids will not have effect on pressure at the base. However, obviously when you take the more material, the total mass of the solids will be added up. But this additional mass is carried by the walls and foundation, not by the floor of the vessel. Okay, so that is what additional mass whatever is there, that frictional force that is offsetting this additional mass, or whatever the pressure is there because of the additional mass, that is taken care by the foundation of the container. Foundation in the sense, let us say I have drawn only hoppers like this only, right, but these things are having a kind of given a kind of support, foundation support with a kind of some kind of cement or a metal poles or something like that. Okay, so these foundations will take some amount of the additional force, additional mass. So whatever the additional pressure that is going to be exerted because of the additional mass, that is going to be taken by this foundation, as well as the friction between the walls and then particles. And then unlike in the case of liquids, for granular solids, high pressure does not increase the tendency to flow. In general, what happens in Newtonian liquid, when you increase the pressure, usually you increase more flow rate comes out, and then fluid may flow comfortably. But that is not true in the kind of solids, especially granular solids of very small size. If you have a kind of granular solids, so when you increase the pressure, what happens? A kind of more compact packing will take place, bulk density will take place, and then they may not flow comfortably. Rather, flowing comfortably by increasing pressure, more compactness of the packing takes place in the case of granular solids, okay, which is unlike in the kind of liquids. In the liquids case, what happens when you increase the pressure, usually you get the more flow rate, okay, comfortable flow, higher flow rate you get. But here in the kinds of grains, when you gradually increase the pressure, what happens, more and more interlocking kind of particles will take place, or a more and more compact packing of material will take place, and then tendency to flow will decrease. So rather, increased pressure packs the grains more tightly together and makes the flow more difficult. So finally, combination of friction and gravitational force at some point in the container causes solids to bridge. In some extreme cases, a kind of bridging of the material will also take place, that something like this, bridge kind of things are there. These things we are going to see in the kind of flowability of the materials because of the bridging. What happens, when you have these kind of containers, if they are forming a kind of bridging, when you take them out, what happens, whatever the material that is there, so let us say you take the material, so some material will be taken out from the bottom, so whatever the material that is there, that is been taken out here, but above that material will be having a kind of bridge kind of structure, they will be still packed. though the bottom material that is there, whatever that has been taken out, the upside material will not flow because of this kind of bridging effect. Okay. So, these things we are going to see when we study the flow out of bins, so that they do not fall even when the material below them is moved. So, when this bridging effect is there, whatever the material below them here at the bottom are the bottom layers of the material, even if you move. So, the material above these bottom layers will not move, they will have a kind of bridge kind of thing, and then they will be kind of hanging kind of form. Okay. Granular solids with angular particles must be loose in order to flow. If you have a granular solids and then if you wanted to flow them comfortably, so they must be loosely packed. The references for this book for this particular lecture are, Unit Operations of Chemical Engineering by McCabe, Smith and Harriet, Unit Operations of Particulate Solids Theory and Practice by Ortega Rivas, Carlson and Richardson Chemical Engineering Series, 2nd volume by Richardson and Harker, Transport Processes and Unit Operations by Giancopoulos, Unit Operations by Brown et al., and an Introduction to Chemical Engineering by Badger and Banchero. But however, most of the details have been taken from this first book, McCabe, Smith and Varret, for this particular lecture. Some of the images presented here in this particular lecture are taken from the second reference book, that is Unit Operations of Particulate Solids Theory and Practice by Ortega Rivas. Thank you.